Hey class, welcome. Thanks for stopping by. We're getting ready to look at, I think, questions 81 through 85. Today in class, we kind of locked in two big ideas. What is a zero exponent? And the other big idea was, what does it mean if I have a negative exponent? And just a real quick recap of what happened in class. If I have, for example, something like x to the a power, and I'm dividing that by x to the a power also, I know that when I look at this, right, one way of seeing this is a giant one, right? This is something divided by itself. So regardless of what x is and regardless of the current value of a, it will be the case that this will always equal the number 1, right? It is 1. The other thing we looked at was this idea that, and we played with it and we developed this, that if you have a quotient and you have a base divided by another base, we came up with this rule, right? This is the same as x, oops, not a, it's the same as x raised to the a minus a power, which is the same as x to the power of 0. Now, because both of these are equivalent to x to the a over x to the a, because they're both equivalent to that, it turns out that they have to be equivalent to each other. So our summary here was that it doesn't matter what value of x that you have, with one notable exception. If you raise that x to the power of 0, you're going to get a value of 1. And you can see a lot of examples of that using our TI calculator, right? If I have, for example, 25.362, and I raise that to the power of 0, I get, oh, that's 1. If I have like negative 32 and I raise that to the power of 0, I get 1. Anything, even like a quotient, like, or a fraction. If I have a fraction of like 5 over 59, I don't know, 5 over 59. If I close that and I raise that to the power of 0, I also get 1. So this is a powerful idea, and it's an idea we want to keep track of. That, oops, you need to go away. That anything raised to the power of 0 is equal to 1. The other thing that we did, and we looked at a lot of examples that kind of build this up. One of the examples I think we looked at was something like, if I have x to the third, and I'm dividing that by x to the fifth. Well, using giant ones, this is the same thing as x to the third over x to the third times x to the second power, right? You can see that the denominator x to the fifth is the same as the thing I wrote, x to the third over, or times x to the second in the denominator there. Well, this is equal to 1, so this becomes a giant 1 in the numerator over x squared. So this becomes 1 over x squared. Now, using our quotient rule for powers, right, I have x, this is the same thing as x to the 3 minus 5, which is the same as x to the negative second power. So we get this idea that if we have a negative exponent, right, if we're raising something to a negative exponent, it doesn't mean that it's a negative number, right? Something raised to a negative exponent is going to be a reciprocal. So, and again, we looked at some examples of this on our calculator. Here's our calculator. If I have, for example, like, let me clear this, 1 divided by 3 raised to the power of negative 2. 1 divided by, this is equal to the number 9. I can make it look like a fraction too if I have 1 divided by 7 raised to the negative first, right? If I've got a negative exponent in my denominator, that becomes just plain old 7. If I have 8 raised to the negative first, this is the thing we were most concerned with, right? 8 raised to the negative 1 power. It's not negative 8, it's the fraction 1/8. 5 to the negative second is not negative 10, it's not negative 25, it's 1/25, right? So negative exponents and zero exponents, that was our big topic push today. And now let's go ahead and switch back to our homework. So this first problem says, what is 4 to the negative first power? Well, if I'm looking at 4 to the negative first, I know from my rules And I know from my observations today that this is the same as 1 over just the number 4. And I'm new. I haven't played with this a lot, so it's kind of nice to just check my work, check my thinking. If I compare that on my calculator, 4 raised to the -1 power, you can see, yeah, it's 1/4. Anything to the 0 power, except for one notable exception, is going to equal 1. So yes, even if you take the number 7 and you raise that to the 0 power, you're going to get the number 1. What about 5 to the -2nd? Well, that's going to be 1 over 5 to the +2nd, which is 1 over 25. Again, we can confirm that with, ooh, I'm hiding my work there behind the calculator. I can confirm that with a calculator. 5 to the -2nd power, and you can see it says 1/25. And the last one is, it's x to the -2nd. Oh, okay, so I can't check that with my calculator, but just following the pattern from above, that's going to be 1 over x to the +2nd power, 1 over x squared. All right, determine the inputs for the following functions with the given outputs. If there's no possible input for the given output, explain why. So I'm supposed to determine what the inputs are. So when I take a look at this, this first one, I'm told that I have the function f of x equals 3x minus 7, and I'm asked to get an output of -1. I want x to be -1. And a technique that works well for me, and your mileage may vary, is if I take the rule for the function, right, which is 3x minus 7, and I set that equal to my desired output. I want the 3x minus 7 to have a desired output of -1. And I solve for x, right? Solving for x here would mean, that would mean taking and adding 7 to both sides. So that would give me that 3x is +6, and dividing both sides by 3, x is 2. So apparently, if I take the number 2, and I plug that into this function, this becomes 3 times 2, which is 6. And 6 minus 1, oops, get out of here. 6 minus 1 is indeed -1. So that works, right? An input of 2 produces an output of -1. Let's take a look at this one. Say I want here, this is fun. I want here an output of 10. Now, we'll talk more about this later, but I know that if I'm taking the square root of something and I want my result to be 10, I know that this thing inside, right, this expression inside, that thing inside has to be the number 100. And there's a specific name for this. We'll talk about it more later. But right now I'm just going to say, look, I want 2x minus 6 to be the number 100. And if I could make that 100, and then I take the square root of it, I would get exactly 10. So I just say, make it 100. Okay, there we go. That thing has to be 100. Therefore, 2x must be 106. Therefore, x must be 100 and... I got to divide by 2. 106 divided by 2. 106 divided by 2 is 53. There we go. So apparently, just this is me checking now. If I take and I say that my input to this function is 53, that's going to become 2 times 53 minus 6. 2 times 53 is 106. Minus 6 is going to be 100. And yes, when I take the square root of 100, I do get an answer of 10. So an input of 53 would produce an output of 10. Let's move on to the next question. It says, which of the graphs below represents functions? Justify your answer. So let's see. Remember, a function is the case where each value of x has no more than one value of y. And I can kind of see that visually here if I just have this ruler that I make set to 90 degrees. That's not possible. There, it's right there. No, that's 89. Close enough, 90 degrees. And as I move the graph along this line, you can see that as it touches on the leading edge here, it's never hitting more than once, right? You can see it's not doing it. In fact, the second one, this W, you can see as it goes along, it's never touching more than once. And why that matters is because, remember, each x value can have no more than one y value. So B would be a function also. And I see the same thing with C, right? As C comes along, oh, nope, I don't see the same thing, do I? Because you can see I can stop in a lot of different places. Like if I stop right here where X is the number 2, I can see when X is 2, I've got 1, 2 different values, right? There's 2 different outputs for this one input. So C is the one that's not a function. So I would say for my answer here, A is a function. I don't need a keyboard. B is a function. And C is not a function. And my justification is for the function ones, each value of X has no more than 1 Y value. And that's for both A and B. And for C, several, in fact, almost all X inputs. What am I doing here? Have multiple outputs. Right, and then the other thing it asked me to do on this is to, for each graph above, state the domain and range. So if I do that for A, and I'm just going to abbreviate here, domain. For A, I can see that there's arrows here, and that means to me that the domain is all real numbers. It goes on forever. The range, however, does look like it's restricted. It appears that the smallest value that this function is going to hit is +1. And the largest value it's going to hit is going to be 2. So I would say that my range values, right, go between 1 and 2. Y values I can get any output between 1 and 2. For B, same thing. It looks like my range is also all reals, all real numbers. And the domain kind of goes up forever, right? I can see because these arrows are shooting this direction, I'm going to be able to hit any value I want in the positive direction. But it looks like the smallest value I can hit, right, is Y is 0. So I'm going to say that my domain is all Y values that are larger than and perhaps equal to 0. So my range is everything more than or equal to 0. And then for this last function, it appears that this one has a restricted domain. It looks like the domain of this function, why I was abbreviating, the domain is all values of X that are larger than, or I guess equal to -2. So you can see it starts right here, right? It's when I get to -2 that I start getting values that are outputs. So I would say that the domain is all X values greater than or equal to -2. And I would say that the range is all reals. And my justification for that is this arrow continues to go up, and it may be slow, it may take a while, but with this going up and the other one going down, eventually I'll be able to hit any number, either in the positive or the negative. Let's move on here. We're asked to write 2 numbers in scientific notation, and this is the first. And I like what we said yesterday in the homework. A number written in scientific notation has 2 factors. One of them is a number between 1 and 10. So there's always going to be some number, right, that has to be in between 1 and 10. Less than 10, but more than 1. And there's also going to be something that is going to be a power of 10. So we've got some value of 10 to, I'll just say, to some power, right? So a number in scientific notation always has to have those 2 parts. And we put this multiplication symbol in between them. It's not an X, it's multiplication. So if I want to write this number in scientific notation, I would write the first part is 1.6. There's my number between 1 and 10. Now, 1.6 is not this large number, right? In order for 1.6 to be this large number, I'm going to have to multiply it by many values of 10. And what's nice about a base 10 number system is every single time I multiply by 10, the decimal gets pushed this direction once. So I've placed this, you can see right here, I've placed the value at this particular spot. So if I multiply it by 1, 2, 3, 4, 5, 6, 7, 8 values of 10, I'm going to get back to that number that I started at. So my answer is 1.6 times 10. I just forgot. 1, 2, 3, 4, 5, 6, 7, 8. 1.6 times 10 to the 8th power. That will equal, those two numbers will equal exactly the same thing. Then let's take a look at B. B is another similarly large number. I know that I have to have a number that's bigger than 1, but less than 10. So it's just going to be this decimal point right here, 5.8413. I'm going to keep all those figures. And then I have to multiply by a bunch of 10s. How many 10s, you say? Well, this time we'll use the beautiful pen of color. So from here, go away, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So there are 10. I need to multiply it by 10 factors of 10. So my answer is 1.5413 times 10 to the 10th power. Moving along, not wasting any time, our last question of the day says, calculate the area of this shaded region. Okay, there's a shaded region here. Well, I do know that the shaded region is the same as this rectangle, like subtracting the area of this white triangle. And the thing I notice about the white triangle is it does have a height of 17. Now I'm assuming a few things here. I'm assuming that this is really a, it doesn't tell me it's a rectangle, does it? I'm assuming this is a rectangle. I'm assuming I've got a bunch of right angles here, and I'm assuming that I can draw this altitude and that this would also be 17 units or 17 inches. So if I wanted to calculate the area here, I can take the area of the entire rectangle, right? The whole rectangle is just 8 times 17. And from that, I can subtract the area of this triangle. And the area of that triangle would be 1/2 times the area of the base, I'll call that 8, times the height, which is 17. So 1/2 times the area of the base times the height. So I'm moving, you guessed it, to my calculator. Where is the calculator? Here it is. Nope, that's not it. This is the calculator. There it is. Let me clear that. And let's do this arithmetic here. So I'm going to have the number 18, and I'm going to no, not 8. There's no 18 here. It's going to be 8 times 17. That makes sense. Minus 1/2. Let me grab a fraction. 1/2. That's nice. 1/2, and I'm going to multiply that times 8 times 17. I always like to try and play arithmetic, but I think I'm not going to this time. I do that's the same thing as minus 4 times 17. Ooh, so I've got 8 times 17. I've got 8 times 17. I'm going to subtract from that 4 times 17. Okay, so that means it's only going to be 4 times 17. It's going to be 417. So if I take 4 times 17, 4 times 7 is 28. Carry the 2, 4. I think the answer is 68. Let me check. 68. That's what my calculator says too. So I would say that the area of the shaded region, right, these two together, the shaded region is 68 square, S-Q-U-A-R-E, inches. Or you can write 68 inches squared, right? That's the area, 68 inches squared. And again, I took the area of the rectangle and I subtracted that triangle. All right, that's it. Sorry, we're at 19 minutes. Have a great evening. This is Mr. Roberts. Talk to you later.